Welcome to another video for Stat 385. So in this video, we are going to cover atomic vectors. So as we've said last time, or last week, everything that we everything in R is an object, and then we saw a lot of objects which are vectors. Those are most of the objects that we will be working with. Their vectors are often referred to like the building blocks of our objects, and so here we're going to focus on objects of the same type, which are referred to as atomic vectors. So these are very much the building blocks of R. And then in the next lecture, we'll talk about vectors or objects that have mixed types, heterogeneous types, and these would be referred to as generic vectors, often called lists. So vectors and lists, both extremely important concepts in R, and if we recall the concept of vectorization from a few videos back, R is deliberately programmed in order to handle and work with types, atomic vectors and lists, and a lot of the programming we'll do will make use of R's built-in functionality for handling those types of structures. Okay, so let's get to the basics. So I have my terminal up, my RStudio is open. I'm in my Stat 385 project. In case I'm probably not going to save anything, but if I were to, then this is where I want to be. Okay, we're going to create a new blank canvas for us to work with. Okay, so let's introduce some familiar objects that we've seen so far. A little character string here. Let's see, 4.2, 42L, slightly different than what before. It's a little bit weird. True. 2 plus 3i, and okay, so we've seen character strings before, character objects. 4.2, just numbers. Number with an L is a little bit strange. True, this logical thing. 2 plus 3i, and raw 1. So these ones we can kind of guess at what the different types would be, but we can check it. Actually, I'm going to be a little bit, so I'm going to use, I have a Mac, and I'm going to use this Option key between Command and Control, and you can see that turns into a cross, my cursor, and so I'm going to do this, and now since I've highlighted all these across these different rows, do type of parenthesis, and then by using command and arrows, I can go to the ends here, okay, and close it. All right. Oops, okay. So now I'm gonna highlight everything and get the type of. Okay, so here we can explicitly see what the types of these different objects are, noting that we haven't stored any of these objects in R, we haven't assigned them a name, and we haven't placed them in our global environment by assigning them some sort of name. But okay, so if we were to do that, this would be the type of the object that we would call. Okay, so we have type of hello world, is a character type. Technically these are all vectors of length 1. So this is a character vector of length 1. 4 with a decimal point is a type double. 42L is an integer. You could probably guess at some of these. It's a little weird to see an L here, but this helps specify or explicitly declare this to be a type integer. Mostly we won't necessarily be too concerned with the differences between double and integer. As we'll see later, they'll both be treated as numeric when we do computations, so it's not that huge of a deal. Type of true is a logical type, and we see complex. We're not going to focus too much on complex in this class again, but the concept may appear in a future quiz, so it'd be good to at least have this in your memory as you progress along. And then there's this raw type, which in my years of programming with R, I have never seen it come up, except to point out that there is a sixth type of atomic vector. So we're just going to ignore that moving forward, and we're not really going to talk about complex. I'm just going to comment those out. Okay. Right, so we have 6 types of different atomic vectors: character, double, integer, logical, complex, and raw. And so we're going to focus on the first 4 of these types, and I've already sort of emphasized that point by commenting out the last 2. Okay, so we've already seen how to create longer vectors of a similar type through the use of the C function. So for instance, if we want to do 2, 5.6, 7.8, then we have a vector of type double. Right, okay. First, let's cover properties of character vectors, noting kind of the order that we're going to work in, which we'll explain in more detail when we get into coercion. Okay, so we have character vector up here, hello world. I'm going to copy it over. We can see that we can specify, create a character vector using the parentheses. The double parentheses or the single parentheses would do the same task. So you can see that even when we run stat385 with single parentheses, it's outputted with double parentheses. And if I do type of, yeah, we get character back. Good. What happens? Okay, so I have character vectors with spaces here. Let's just try one more without a space. So this word foo is just kind of programmer jargon. They usually refers to some sort of variable name that you don't really care about. It's just something that's a placeholder for something else that may be more interesting. So here we're just demonstrating concepts, and we're not gonna, we're just using a nondescript name here. Okay, so character. So this works as a character vector. And what happens if I do this? This is, of course, we understand to be sort of nonsense. We haven't declared anything on the global environment. It looks like gibberish, so perhaps it's a character vector. No, it complains. Okay, so what happens? So basically so the parentheses, single or double, are very important for specifying character vectors. If we just input words and then try to call them, then R is going to complain. Why is R complaining? Because what this to R is look in the global environment for an object with the name foo. Okay, so we've been calling these things X, which is usually some sort of variable name and whatnot in mathematics or whatever. And but here, anything that's written out in this way, R thinks to go look in the global environment and find it. So if we had this, now if we specified foo, then we would get this is a name of an object that we've assigned the value 5 to. Okay, so I'm just gonna go back and clear the global environment. Okay, so just like we saw before, we can create longer atomic vectors of the same type. This is a long character vector. Okay, so I have a vector with 6 elements. They're all strings, and we can see what the elements are by calling it, and then we can see that yes, indeed, this is a character vector. Okay, great. And then, like anything that we've seen before, we can, I should say that as in the case of numeric vectors, we can give these different atomic vectors we can assign them names and store them in our global environment. And here's that fun word foo, bar, baz. So this is like a programmer's alphabet of non-descriptive variable names to indicate that these are sort of, we're doing tasks and we're going to throw away these variables later. I should be careful to call them variables. These aren't variables. They're names that reference a object that is stored in R. Okay, and then they point to the object. Okay, and then there's one more, typically, and then I don't know what the this alphabet is after clocks. Okay. So we can see that, yes, we can indeed take character vectors, character strings, and store them in R as vectors, assigning them a name, like we've done previously with numeric objects. Okay, so staying within the theme of combining things of the same type, this is getting a little bit ridiculous, but nonetheless. So we have type of foo. So this is a character, right? So I could do as bar. Okay. So now this is a character vector because everything in it is a character. And this could just get crazy. But anyways, so long story short, we're creating vectors of a similar type, in this case character, and we can see how we can kind of, create these things, store them in R. It's very similar to what we've done in the previous lectures when we did the same task with numeric vectors. Okay. All right, and then if we want to, sometimes it seems like, okay, so in this lecture, this is a lot of like very foundational, very important concepts that will come up throughout the rest of your career if you keep programming in R. It just, introducing all of them, it seems very, very tedious and kind of like simple, but I guarantee you that this stuff is incredibly useful, and if you follow it, will very much reduce the amount of errors that you run into, and can allow you to check for things when errors do come up. So like this function here would just check to see something is of character type. So if I were to, create a string here, then it will tell me whether or not this inputted object is in fact a type character, and it is. So you can see, hinting ahead, there's a type called logical, and now this function checks to see whether or not a specific object is of type character, and then returns a logical element indicating whether or not it is the case. In this case, it is true. So let's see what happens if we just put in Baz, which is our long character vector up here, and you can see that this is indeed a character vector. Okay, great. All right. Okay, so now let's get on to double vectors, not two vectors, vectors of type double. Okay, so I don't want to say vast majority. Well, I do want to say vast majority. Vast majority of numbers that we will encounter in R will be in the form of double vectors. And double vectors store floating point values. Is where the concept comes from. And just to demonstrate, we can see if we use this question mark dot machine, we can see kind of the numerical precision of your computer in base R. And to get a little bit of information about, the double elements. Actually, I don't want to question mark it. I want to actually display it. So for instance, we can see this right here is the smallest difference that's detectable between two numbers in R. So we sort of saw this before, or I mean, we didn't see this before, but we saw the idea of wanting to express real numbers inside of a computer, like the number pi, which is irrational and therefore has an infinite string of decimals in a non-repeating pattern. So of course that number can never be represented inside of a computer with only finite number of bits to store the number. So there's always going to be some sort, if you're doing those types of numbers, there's always going to be some sort of like finite representation of it, and this just kind of gives us the rules for how, or it kind of gives us the level of coarseness or fineness for these the numbers that we can actually work with in R. Okay, so we have, you know, the smallest number that we can create, or the smallest magnitude value, the smallest, the largest value, so forth and so on. Okay, so this is not a course on finite precision. This is not a computer science course, but nonetheless, it's something that exists. Okay, so double vectors are, you can think of them as decimal valued numbers, and with the idea being that they can represent real numbers in mathematics. Okay, anyways, getting down some tangents. So type of, you know, say this type of number is double. We can represent numbers in scientific notation. So this right here is just a very, very, very small number, also of double. Type of, and if we don't specify the L after 6, then we get a double. And for a lot of tasks that we'll work with, and most of the tasks that I've worked with in R in my experience, we don't really much care about the differences between double and integer values. Okay, and just to bring back our sort of motivating example, type of pi, double. Okay, great. There's also a few other numbers that you'll sometimes encounter, sort of a divide by 0 and kind of the conventions that we work with R. So 1 divided by 0 is infinity. You know, mathematics requires you to specify or choose a convention, and here R has chosen a convention for you. -1 divided by 0 is infinity, and then 0 divided by 0 is not a number. All seems like pedantic and trivial, but it is something that comes up when tasks run awry. These are values that you sometimes will get, and then seeing where they come from and seeing what created them is important for debugging programming. Or yeah. Okay, so so sometimes it can be tedious to create vectors that have like a repeating pattern. Say I want to do something like this and so on. I'm going to comment that out because that won't run as code, right? But if I want to like iterate out from 0.1, 0.2, 0.3 all the way to 1, say, for instance, then there is a command that would do that for us. Sequence, SEQ, short for sequence generation, I guess. Yeah, so we can start from equals 0.1 to equals 1, and then we can give it a length to iterate by equals 0.1. Cool. Okay. Or if you want to go from 0 to 1, you can also say you want to go by 0.05. You can do this in two ways. You can directly specify by, or you can do length equals 21, and this would just construct 21 evenly spaced values between 0 and 1. In this case, since we've, yeah, okay. All right, so both the same values here. All right, so for additional details on double, we can use our question mark and go to the help page. So double precision vectors, there's a little bit of detail on it. And then, yeah, it even references the machine thing that I was talking about earlier so that you can see kind of the precision that your version of R and your computer work with. Okay, very, very nice. All right, so we have this similar thing. This is double checker. 4.2, nice. And let's try it with cat. Sure. Doesn't work. Okay, so great. So we're covering logical values too as we go. That's great. So we have, as sort of a special case, we'll cover integer vectors. All right, so as we saw earlier, the computer recognizes 42 as a type double, but we can override the specification by including this L on it. Okay. So this is a little bit in the weeds, but nonetheless, we can see that R does have a special, or does declare integer as its own unique type, and so that we can write atomic vectors with integer type. And just like we created sequences up here, sequence generation, we have a special shorthand which does come in handy quite a bit for sequence generation for integer values. So 1 colon the number you want to get to, and we can see that this does create a sequence of integer values from low end of the sequence, 1, to high end of the sequence, 100, and all the values in between, of course. Let's just check it out. Let's see what the type is. Okay, integer. So note that, I know that, we talk about this and then we go really fast, but I'm hitting Command Run here to display it in the console. And if I highlight the what's being treated as the argument of this type of function, the sequence, I can hit Command Return on the highlighted quantity to get the sequence itself. Okay, so that's good to have the little refresher. Interesting, and I don't come across this too often, but you can do this same type of sequence generation shorthand for, say, start at a double value or an integer value 1.1, and then iterate by 1 20 times, essentially. Or I shouldn't say iterate by 1 20 times. Get a vector of length 20 with 20 iterates, including the value you started with. So here we have a length 20 vector. That is going to be, I think, type double would have to be. Yes, okay. But you can see what it did here. So I've seen this mostly come in handy when you're creating sequences of integers, and not these. Okay, so I'll comment it out. All right, and if you want to get more detail on what this colon operator thing does, we can do it. Cool, from A to B. Nice. Okay, so getting further in the weeds on type. So we're covering atomic vectors, vectors which contain objects of the same type, and we've shown that there's 6 types in R, and we're going to focus on 4 of them, character and logical being on the outside, and then right now we're in the weeds on double and integer. And I've said that those, for day-to-day operations in R, those things are very, very similar. So I'm just going to drive that point home by talking about the mode, or the storage type of an object. Okay, so if I have 42, which we saw above is a double, and mode 42L, which we saw above was an integer, they have the same mode, which is just like class numeric in this case, class being something that we will cover in more detail. But yeah, so here from day-to-day operations, let's just see what happens when we do this. So, okay, so it knows how to do adding these two quantities and spitting out something that's familiar to us. I'm guessing it's going to be double? Yes. Okay. Interesting. Fun stuff. Okay, so we have specific checker functions for whether or not an object that is supplied is indeed of the specified type. Wait. Oh, no. Oh, that converted it to integer. Yes. I wanted this. Is.integer. Okay. Is.integer 42L. Okay, so false, true. Now I'm interested. Okay. So this should convert that to type integer. let's just see. Cool. Okay, so this actually does come in handy. This is kind of a bit of a tangent, and we'll talk about it later. Let's do this. So occasionally you'll have a character vector, or you'll have a character vector which will be a number, and this as dot will convert that into a number. Use as dot double, or if you want to just work broadly, as dot numeric. And let's just get rid of that just to demonstrate the point. So usually in day-to-day operation, I've used this quite a bit. This actually comes in quite in handy very often, because sometimes you'll work with somebody's CSV file, and just due to the bad formatting that can have when you communicate those things with R, you can get like a string of or a column which is all numeric, but for whatever reason it's inputted in R, it comes back as a character vector. So converting from character to numeric is something that is extremely important. So this is actually very helpful for that. But this is now in tangent territory. Okay, anyways, but it's nonetheless very, very useful stuff. Okay, so this type stuff in atomic vectors, it's very, very tedious. I can see how it could be a bit boring, but it is extraordinarily important. And mastering it, you'll have to come back to it and go through this quite a bit. I'm not saying necessarily watch the video again, but you'll have to reference this material again. But like this is where a lot of like error debugging comes in handy. This video, and then especially the next one as well when we talk about coercion. Okay, so oh man, logical vectors. Okay. So type of, so true is a logical vector with one element. And again, yep, we can see logical. And then the other major logical value is false. Okay, and then there's also one more. NA, which is logical or not applicable. This is kind of its own very important thing. And so we will come back to this. It's very important. Again, this is another thing that NA values come up all the time. Again, I'll just refer back to my example of somebody hands you a CSV file and you want to load it into R and work with it. If data is incomplete for a subject, like if you imagine column names consist of things that are measured on an individual and row names are different individuals, then occasionally you don't have all of the measurements for an individual, and sometimes that would just be converted into NA values when you load it into R. So something that comes up quite a bit. Okay, so true and false are these logical values, but they're also reserved words in R. So I can't, and you can see that they are highlighted in this blue text on my editor. So I couldn't just give them a value. R is going to complain. Interestingly enough, T and F are often used as shorthand for true and false, and they do, as by default, reference true and false. This is one of those things where I don't recommend calling something that you want true just capital T, because, and one reason is because these words are not reserved. So I can take the numeric object 42 and call it T, assign it the name T. You can see the global environment changed. Same thing with F. Okay, so I don't think that people are this evil, but you could do this. T equal, or take the character vector for, actually, you know what? Even worse. Why would I even do that? It's the most evil thing you could do. Take false, which is a reserved word in a logical value, and assign it the name T. Oh, gross. Okay, so then you can see that is not logical. All right, so I did preserve that. Ugh. All right, fun stuff. Okay, so if you want more information on which words are reserved, i.e. can't be, you can't take an object and give it one of these names. You can see here. Oh, pretty short list. Okay, I'm sure there's more. Okay, and since this evil construction they're both the same type, I can do CTF, and it is indeed flipped. I'm just gonna comment that out. Let's just really comment that out. Okay. So anyways, I can have a string of logical value. I shouldn't say string. I can have a atomic vector of logical elements. And you can see it here. This will come in handy when we discuss indexing, which we're actually about to do, but in a lot of detail, or like in more detail when we want to do like subsetting of a data table or data frame or matrix or something like that. Okay, so anyways, I'm going to borrow some code as we go into length, and I'm going to say basic indexing. I can already tell that I'm going to go on a tangent to intermediate indexing as well, though. Okay. So let's get some code that I have conveniently obtained. All right, so what I'm going to do here is I'm going to create a vector of integers. Well, I should probably convert it to type double. Anyways, I'm creating a vector of elements starting from 2, ending in 100, and going by equals 2. So these are just even numbers from 2 to 100. Okay. Type of, yeah, that's what I thought. Okay. And then similarly, I'll create primes. Okay. So, I mean, you know, we can kind of guess. Oops. Command Z, Command Z. We can, you know, count this up and see how many elements are in these vectors. However, it is much easier to just remember the length command, which would then return the number of elements that each one of these vectors has. Okay. So printing out the evens vector again, we see these, and you may have noticed this, and we've actually talked about it a little bit. We have this, when we're calling these elements, or these commands and these objects, you'll notice that there's this 1 here. And then with the evens vector, there's a 1, 24, 47. This is where, so the object itself is a numeric vector. I'm over here for evens. It's a numeric vector, technically of type double, of all the even numbers from 2 to 100. It's stored in R. Then when I'm calling it, this is giving some sort of representation of that object to the user in a way that is, I guess, somewhat convenient to read. And so what this is some indexing for the order of the, for the elements in this atomic vector. So here we're starting at 1. So the first element of this numeric vector is the value 2. The second element of this numeric vector is the object 4, so forth and so on, and we get to the 24th element is this numeric element 48, and we get 47. 47th element is 94, 48, 49, 50. Okay, so this is just, you know, so we have an index for each one of these elements. So one little thing to note here, well, I shouldn't say little thing if you have a background in computer science or other programming languages, which, and this may be a little bit confusing, is that R is a one-indexed language, which means that the first element is given the index 1. So if I were to, you know, let me go up here. So the square brackets here will allow me to pull out elements from the atomic vector. And so this specifies I want the first element. And so in this case, first element is 2. Your computer scientists may be tempted to do evens 0, which is not a thing. It doesn't exist. The 0 index is not what R is. So this just complains. It says, oh, this is a numeric vector, but it's just, this is empty. It doesn't have anything. Okay, so it's a reference that went awry, which this is an error message, or this is a thing that I see all the time when I'm programming. Is one of the most annoying things in my day-to-day life when I'm writing code and functions and to do statistical tasks. Okay, but on that point, I am using R to do statistical tasks, and it is a language for statisticians by statisticians, and referencing the first element of an object by the index number 1 is something that is very natural in statistical mathematics, linear algebra. Like the first element of a vector, or vectors are usually, when you're talking about their size, you're talking about their elements from 1 to n. So, and similar idea with matrices. So it makes sense that a programming language by and for statisticians would adopt this naming convention. And that isn't to say that this is superior in any way to 0 or that there aren't reasons for it. I'm not a computer scientist, so I don't know them, but I do know that the reasons exist for such a indexing convention. Okay, right. So, so we can, so we can pull out specific elements using the brackets notation. Now in generic lists, which we haven't covered yet, or sorry, generic vectors of different types, it's a double bracket, and here this notation will also work for atomic vectors. So, right, the 20th element of the even vector is the object 40, and in this other notation, it's the exact same value. So this is a more robust general indexing strategy. One thing that comes up quite a bit is wanting to extract the last element of a vector. And this is important whether or not the vectors are, increasing or not. Actually, it's important more often when, numbers are just kind of in some sort of random ordering. But if I want to do that, check this out. I can do evens. Actually, let's write it this way. Right, so this is going to pull the length of the vector. So the vector has 50 elements in it, and if you want to think generally, the vector has this many elements in it, and I want the last one. So I can specify that I want to pull the last element here. See how that worked? So evens had 50 elements in it, and this returned the value 50. So if I were to do something like evens equals, this is getting a little bit hairy, or a little bit tricky here. Okay. Sequence from equals 102 to equals 224. I mean, it's all, we're always going to know the length, but nonetheless. Okay, so what is this going to do? So I have a vector, a numeric vector, technically of type double, and I'm going to combine it with another numeric vector of type double, creating a vector of type double. If I've thought correctly, this is going to be the even numbers from 2 to 224. And be careful with this sort of assignment. I'm building on to something that already existed. So this is dangerous. Okay, so, but I want to demonstrate this point. Okay, so what happened? So I changed evens. Just make sure it looks okay. 100, 102, 104, 100, okay, good. Okay, so now this command here will still work and pull out the last element. So it doesn't really require, this doesn't work just for one particular, atomic vector. It works for all of them, or this strategy. Okay, and similarly I could do, this probably would have been easier to demonstrate. Yeah, so we can get the last element of the primes vector as well. I'm going to keep these two things separate. Okay, great. Cool. All right. Cool. If I want, we can use a vector command itself to initialize a vector of a certain type that we may work with for some future use. The default value for a vector of logical is false. If I do this with mode equals integer, I get a vector of 3 zeros. And if I want to do, switch it up a little bit in the length, I get empty character strings. All right. Okay. Let me just, and if I don't provide a length for, let's say, a integer vector, then it's just going to essentially say, well, you've created an integer vector. There's just nothing in it. There's no elements. Okay, which is very similar to null. So somewhat, yeah, related to the concept of the zero length vector with, a set type, there is a null element, if you like, that represents absolutely nothing. So it's like kind of like just the empty set. You can imagine the empty set in different sort of mathematical structures, mathematical spaces, if you like. It's always, same notation and for different sets. You have an empty set for, collection of integers, you have an empty set for a collection of real numbers, so forth and so on. Okay, so, right, so this is nothing type of null, great. Length, null, 0. Okay. And let's try 1, null. Okay, just got rid of that value completely. Okay, and so if we have a atomic vector without, so that we've seen the C function to combine elements of a certain similar type, when we don't specify it, it creates a object of null. There's no type specified, so it doesn't complain, it just returns nothing. Okay, last but not least are attributes. And this is just metadata that we can assign to vectors in a way to give them some sort of clarity about what's being returned to us. So, for instance, if we just work with a sequence of a meaningless sequence of numbers, then nothing is actually going to be specified as an attribute. Now I'm going to take some code that I have laying around. Okay, so let's say I create, very similar to this, I create a vector, just a vector, and it does not have any attributes by default, right? But I can, and never mind, okay, we will get into lists very, very soon, but never mind this. What I'm going to do is essentially assign attributes, assign information to this vector using this command. Okay, so now I've specified some attributes, and we can see that we do have that specified. I could just say a vector from 1, 2, 3. Man, this is getting corny. All right, great. Okay. So one more useful form, I shouldn't say more useful, I should say more often used form, would be to give names to specific elements in a vector. So what I'm going to do, so again, this doesn't have anything assigned, right? There's no names here. This is just a meaningless vector of elements of type double, or just a numeric vector if you like. Okay, so now what I can do is give it, so it has no names right now, I can give it names in the form of characters. Okay. So now what happens when I call vec? You can see that the elements of the vector are given name. This is the exact same vector for all practical purposes. So vec, if we go to our global environment, I've been creating stuff all the way throughout. You may have seen it change. You can see that a vector, which is 1, 2, 3, and vec1, which is 1, 2, 3 without the space. We'll just add the spaces just to make it all the same, even though it doesn't matter. So a vector is just nothing. Let's just, assign 1, 2, 3, get rid of the attributes. If I do this, I'll add the attributes back. But right now, so a vector is 1, 2, 3. Vec1 is also 1, 2, 3. It's a numeric vector with 3 elements. Each one contains the elements 1, 2, 3 in order. Okay, there's nothing, so they're exactly the same. It's just this one has some additional metadata where the other one does not. So a vector, you can see, doesn't have the elements named. This one does, but for all practical purposes, they're exactly the same. So if I were to take a vector and vec1 and add 1 to each of the elements like we did before, then you can see that 1, 2, 3 became 2, 3, 4, and here you can see 1, 2, 3 became 2, 3, 4, but the names are preserved, which in this case is somewhat problematic. Well, no, it's fine because it's just indicating the positions. Okay, so this may seem kind of silly right now, but it's kind of cool because what I can do is I can, if I know the names well enough, I can do stuff like this and pull the second element right out by just calling the name directly rather than the index number. Where this becomes useful, let's say I have something that evens. So evens is long. Yeah, right. So let's say I do this. I can assign the names directly too. I don't have to. So what I did here to give the names was have the element, then add the names. Here I can just actually do the names directly. And this is going to be more interesting. Let's call it mean x equals mean of evens, SD x equals SD evens. Okay, so now I have a new vector. Oops, yeah. Why did I do that? And so you can see here that if I was to do some kind of complicated, interesting statistical task, then now I have names that are descriptive, so that the mean of whatever I was doing, the average, is this value, and the standard deviation is this value. So that's kind of cool. So that's, you could think about function calls. If you do complicated tasks, then maybe this kind of convention is useful for providing names of your output. Okay, so this is a lot of information. Some of it seems tedious and boring, but it's not tedious and boring to save time and know how to debug error messages, or rather, that is tedious and boring, but you're going to spend less time doing tedious and boring things provided you've learned these tedious and boring things. And that I can tell you, if I were to have grasped these concepts quicker, I would have more time to do fun things rather than the tedious and boring things such as debugging. Okay, so very, very, very important. Thank you for hanging in there, and I will see you next time. All right, bye.